All right.
What
What's
you were
that?
listening to it? You were
We're
listening
listening
to
to the 1960s Doctor Who.
Oh,
So
okay.
these are episodes that no longer exist in video form. They
Yeah,
exist
I
in
know.
audio form only because super fans recorded them on their reel to
Yep.
reel. Apparently, the one guy like I had dangerous electric hookups to get the microphone as clear as
Wow.
possible. So yeah. All right. So we've waited a good 10 minutes for the regulars to show up, but Rick's here. That's fine. We're gonna go through the direct. We're gonna finish this up. We talked about the Dirac delta function in quotes yesterday. This is an example of a distribution. There are other famous distributions in math that are often defined in these sort of curious ways. That'd be a nice project. But yesterday we sort of finished by proving the sifting property. Uh, so what we think of is we think of this Dirac delta function, t minus a, as taking one unit, right, sort of a one square unit, and blasting the function with that at exactly one moment. Okay, so it's an instantaneous unit impulse, and if you multiply that by your function and integrate it, it sifts out the value f of a. Okay, so all right, so we proved this yesterday. Um, Now, because of symmetry here, the Dirac delta is a symmetric function. It's symmetric about the center, t equals a. So, it doesn't matter how you put that in there. Um, we can think of the direct this integral, right, then as being the convolution. Okay, so when you convolve um, the function with itself, you get the original function back, which is a very interesting property. So this Dirac delta, in addition to having the sifting property, it acts like an identity. It acts like an identity for the convolution operation. Okay, so once again, you've got this symmetry here. You can reverse the subtraction, and therefore, when you look at the convolution integral, this is the convolution integral we had, it works like that. Okay, and what that then really talks about, or what that really says, since this is sort of an identity, is you can think of your function f as being a sum of impulse responses. So once again, if you think of this function when you sift it out, right? When you sift out the individual function value, you can go through your whole domain and sift out each individual value. So looking at it this way, right? F of t is f of t convolved with the delta. You're looking at f of t as being the sum of all of these little unit impulses at each and every little value. Okay, uh, it's it's an interesting little thing. So once again, this is another way you can really go about defining the Dirac delta as being this identity. So in this particular case, we can use that sifting property to find the Laplace transform. So if I wanted the Laplace transform of the Dirac delta, t minus a, that's the integral from 0 to infinity of, and now we'll just go through the definition. That's the function here, delta t minus a, e to the minus st dt. And now we can just use the sifting property. Right? I'm integrating with respect to t. I've got the Dirac delta of t minus a. This is just going to sift out this function evaluated at a. This is e to the minus sa. So that's our property. Okay. In particular, if a is equal to 0, so if I look at just the Laplace transform of delta of t, then a equals 0, so e to the 0, then that's just 1. Okay, so that's the Dirac delta, the unshifted delta goes over to 1, and we'll talk about the importance of that here in just a minute. So let's look at this example here. Solve the IVP y double prime plus 16y equals delta of t minus 2 pi, we've got initial conditions 0, 0. So let's talk about what's going on with this. This is sort of the very bare bones example here to show you what this Dirac delta does. So if I look at the initial conditions, y at 0 and y prime of 0 is 0. So that means that, if I go to start, whoops, I guess this is the t-axis here. If I go to start with this, y at 0 is 0, and y prime at 0 is 0. So that means that we're at the origin, and we got a slope of 0. So we're starting off at the 0, and we're flat. Okay. We've got this piece, which is going to correspond to some oscillations. And then what happens is, at some point here, t equals 2 pi, we have this unit impulse into the system. All right? So t equals 2 pi, we're getting this blast into the system, and then we'll see what happens. So when we go to graph the solution here, something interesting should happen here. So let's find out. All right, so we're going to Laplace this over. We've got our formula here for y double prime. So that's going to Laplace to s squared times the transform function y minus s y of 0 minus y prime of 0 plus 16 times the transform function y equals, and then this is what we talked about today, courtesy of the sifting property, this is going to be e to the minus 2 pi s. Now the initial values here, y at 0 is 0, y prime of 0 is 0, so that's gone. I can factor out capital Y. And then I can divide that over. So hopefully, thinking back to what we did last week, when you have this exponential showing up, that corresponds to a unit step shift when we come back. So it'd be e to the minus 2 pi s over s squared plus 16. All right, so here we go. I'm going to inverse Laplace. I'm going to go back to y equals, and we got to inverse Laplace this, okay? So let's once again kind of review how this works. This is another kind of shift here. So this exponential coming back, this is going to come out as a unit step. So it's going to be a unit step of t minus 2 pi times the inverse Laplace of the thing that doesn't have the exponential on it. But the t is going to get shifted to t minus 2 pi. So y equals unit step t minus 2 pi. Whoops. And then here we're going to bring this back. So we've got a 1 over s squared plus 16. The fact that it's a plus down there means we're getting oscillations. The fact that it's a constant and not an s means it's coming back to sine, but we'd have to we got a frequency 4, and we got divided by 4. And t then is shifted to t minus 2 pi. And once again, when you shift these trig functions, especially when you shift them by units of pi, it's worth the time to simplify these things. If you have the sign, this would be 4t minus 8 pi. Right? You think back to the unit circle. 8 pi is going around the unit circle 4 times in the opposite direction. So this is basically 4 revolutions clockwise from the original position. Anytime you go around a complete revolution, the sine and cosine functions are back to their original values. So we can actually simplify this to sine of 4t. So even though when you look at the answer there, it looks like you didn't shift that piece, we actually did. We just simplified the shift. And so for our final answer then, we get y equals, we got this unit step t minus 2 pi times, and I'll write it as 1/4 sine of 4t. All right. So I can write this as a piecewise defined function, okay? Because for the unit step t minus 2 pi, for t between 0 and 2 pi, the unit step is actually 0. So this would be 0 times a quarter sine of 4t, which is nothing, right? So this hasn't switched on yet. And then for t bigger than or equal to 2 pi, the unit step is 1. And so another way to write our solution is that it's a quarter sine of 4t for t bigger than or equal to 2 pi. So this system starts off at nothing, going nowhere, until it gets to 2 pi, and then that's when the impulse hits the system, and that causes the sinusoidal motion. Okay? So that's the effect of the impulse. And the take home for next week, which we'll talk about here in a minute, has some of this built into it as well. Okay, so last time we started doing this. So solve the following IVT in terms of convolutions. To get the impulse response, let's let f of t be delta of t. So if you recall here, when we solved this generic IVP yesterday, we had like the YP piece was, we had this inverse of 1 over AS squared plus BS plus C convolved with F of T. And we were like, okay, we're going to come back and talk about what this means in light of the unit step. Okay, so if you think about it, look at what happens here. If we replace f of t with the impulse, so this is kind of a generic version of the one we just did. So we just have the unit impulse, but we're going to just start it at 0 there. Okay, so we're going to just blast this thing at t equals 0. Look what happens. If I try to solve this, and I Laplace this over, then I'm going to get essentially the same thing I had yesterday on the left-hand side. I'm going to get my AS squared plus BS plus C, y, equals, and then we'll have the stuff from the initial conditions that feed into the YC, which I'm not going to write that down, plus the Laplace of this, which is 1. And so we're going to have the stuff that's going to factor into the YC plus 1 over this thing. Oops, AS squared plus BS plus C. And so this is what's going to come back for the YP, right? This is the term that's going to come back to the YP. And so I can think of this term this is my unit impulse response. So in my generic formulation, where we had the yp coming from this convolution, I can think of this as what I'm putting into the system, right? What the input to the system being convolved with the unit impulse response, right? Sometimes this is called a weighting function. So it's the weighting function, which is the unit impulse response of the actual system. So like if this represented a circuit, for instance, okay. So this kind of gives more context to what that piece is actually doing. Okay. All right, and then there's your homework for that you can work on. So let's take a look at, so you've got the take-home in test 13 due tomorrow. Let's take a look at what's coming up for you next week. I want to walk through, because one of these, once again, this is kind of like your last one that's got Laplace transforms on it. So you're gonna have a test 14 and a take-home 14. These will still be on your Laplace. Oops. This will be finishing up Laplace transform. And then you're just going to have a take-home 15. This will be 25 points. This will be over the Chapter 9 stuff that we'll get into. We'll start tomorrow. We'll finish it up early next week. Chapter 9 is just higher dimensional versions of Chapter 5. So we spent some time yesterday reviewing the Chapter 5 ideas. So those are just going to come over in higher dimensions for Chapter 9. And then the other 25 points, that's your project. And we talked about the project, I think, last week, how that, if you have questions on that, just let me know. So let's take a look at Take Home 14. So there will be no test 15, is what I'm telling you. There's no test 15. Okay. Take home 14, we start off with a very standard sort of thing. Find this integral using Laplace and inverse Laplace transforms. So hopefully you recognize this integral as a convolution. So we did one like this in class. We recognize it as a convolution. We Laplace it over, do the usual stuff we do, and then bring it back. Okay. You can check your answer by integrating if you want, but I want you to sort of use the Laplace and inverse Laplace to do that. All right, and there's not a lot to do there. It's 5 points. The only reason why I left all of this blank is because I didn't want it to, because this is going to take some space here. So it turns out, here's a property of Laplace transforms. It turns out if f is periodic with period t, so that's what this means, then you can figure out the Laplace transform by just looking at basically integrating over one period and then adjusting this way. So for example, who are some of the most famous periodic functions? So Rick's the only one in the audience. Rick, can you think of a periodic function? Classic periodic functions?
Fourier.
Yeah, and those use the sine and cosine, right? So for example, I'm not going to do this one, but let's do cosine. So cosine of t, the period of cosine of t is 2 pi. So according to this formula, the Laplace transform of cosine of t, instead of doing what we did, which was kind of a bit of a cheat, we used the formula we got from Cauchy, which we got from linearity and exponentials, okay? And then we just switched in the imaginary number. if that made you uneasy, we could find it this way as well. To get the Laplace transform of cosine, according to this, it would be 1 over 1 minus e to the minus s capital T, which is 2 pi. So 2 pi s times the integral from 0 to 2 pi cosine t e to the minus st dt. Okay, and then this would require integration by parts a couple times. If you had me for Calc 2, this was one of the problems I gave you to do because of the Laplace transform stuff that I knew was coming later. But anyway, and then you can actually work this out. And this should actually then come back to the same formula that we know and love. So on 2, part A, all I'm asking you to do is do the same thing for sine. And then I got this little footnote. Feel free to use this formula. So you don't have to go through the parts twice again. Just go ahead and use this formula to help you with that integral. You follow? And what you should find is by using this with sine, right, this should work out to be, you know, whatever, 1 over s squared plus 1, okay, which is what we normally get when we Laplace sine. So this is just verifying that this formula will get you to the same place that we got when we looked at the Laplace of sine. And then for part B, we're looking at the Laplace of the sawtooth wave. So where this property it gets used quite a bit is, you know, when you put different signals into a circuit. So here, the sawtooth wave, f of n equals t minus n on the interval n to n plus 1. So we start off with n equals 0. So you know, you want to graph this out. So when n equals 0, we're going to look at 0, 1, 2, 3, 4, etc. Okay. F of t is t minus n on the interval n to n plus 1. So when n equals 0, we're just going to get the function t from 0 to 1. And then when between 1 and 2, we're going to get t minus 1. And then from 2 to 3, we're going to get t minus 2, etc. So here's why this is called the sawtooth wave. You start off here, and you're going to go up to there, and then it's going to switch, come down here, come down here, and so on. Okay. So this is periodic. It repeats itself how often? And you can find the Laplace transform doing this, okay? So the whole idea, right, if you look at what's going on here, the big idea about periodic functions is that since they repeat themselves every period, you should be able to determine everything about the function by analyzing one period. And that's exactly what's going on here. We're just integrating over one period and then making that adjustment. Now you might wonder, well, where the heck does this come from, right? Where's that magical thing come from? Well, guess what? That's number 3. So number 3, we're going to get to prove property number 2 by working through the following steps. Step 1, explain why the integral from 0 to infinity of that periodic function would be the sum of the integrals here. My advice is to start here. Start with the right-hand side and write it out. Once you write this out, you'll see exactly why this is happening. Okay, this is the additive interval property of integration. And you can go ahead and assume all these things converge. Okay. Next step, make of change of variables. Let u be little t minus n times capital T. Remember, capital T is the period, which is a constant. N is a natural number, which is a constant. The thing that's the variable in the integral is t. Now I'm going to let u be n minus t. So that t is u plus nt. Use the fact that f has period t to explain this now. So notice what's happening here. We're doing the change of variables. All right. So start with this, use this substitution, and explain in particular why this happens. All right, because you notice now suddenly that NT just sort of disappears. What's happening up here, you see in the next, this is the standard sort of substitution stuff, okay? So explain this happens, and then what happened to this, right? Why can you bring that out front? You follow? So it has to do with what's the variable, what's the constant, and periodic. And then finally, we've got the geometric series formulas. This is something you typically do back in, we typically do it like in pre-calculus. I think they talk about this a little bit. You know, this is how you formally can prove that 0.9 repeating is 1, for instance, right? So if you're looking at adding these pieces up, you can rewrite them this way, and boom, what comes out? Okay, so the geometric series formula is as follows. Okay, if you are adding up a geometric series, a plus ar plus ar squared, blah, blah, blah. This ends up being the first term a over 1 minus the common ratio r. So you can apply that here to get that. Okay, so that's the geometric series formula I want you to use there. And then finally what you do is then you can weave all of this together. You start with this, that's the definition of a Laplace transform. And then you've justified why you can write this as the sum of these integrals. And down here, you've taken each of these integrals and you've replaced them with this. This has nothing to do with n anymore. The integral now is completely independent of n, which means you can, in this summation now, you can take that out front and then you'd be adding these up. So then you just basically piece all these together in one continuous equation. So you justify each of these individual steps and then write it out into one formal proof, and then you've got the proof of this property. Okay. And once again, this is an important property of the Laplace transform. I don't think the book does it. This is why I've made it a homework. But it's really important if you're doing signal analysis because of these sorts of things, like the square wave, and the sawtooth wave and things like that. Okay, so that's the kind of nonsense you'll be doing on that. Okay, so that's due a week from Wednesday. And then you got your test 4, which is over the other stuff. And then that'll finish up our unit on Laplace transforms. Okay. All right, so that'll do it today. Rick, thanks for tuning in. Tomorrow we'll start the Chapter 9 stuff. So we'll go back and talk about what if we have a third order derivative, fourth order. How do things like undetermined coefficients and variation of parameters generalize? They generalize exactly as you would hope and expect they would do. So we're going to end the course reviewing some of the meat that we had in the middle. So thanks for tuning in. Have a great rest of your day, and I hope to see some of you tomorrow.